Hello there, Mr. Sutton here, bringing you the AB Calculus 6-8 Extra Practice number 2 solutions on motion free response practice. For this free response problem, we have rocket A with a positive velocity v of t after being launched from an initial height of 0 at time 0, and the velocity for the rocket at selected values is given in this table from 0 to 80 seconds. Our first task is to find the average acceleration of rocket A over the interval 0 to 80. So if we're finding the average acceleration, we're essentially finding the average rate of change for velocity, because acceleration is the rate of change of velocity. So if I'm just finding a rock for velocity, I just need to do v of 80 minus v of 0 over 80 minus 0. V of 80 in the table here is going to be 49. V of 0 is going to be 5, so we have 49 minus 5 over 80 minus 0. And let's see, that's just 80 down there. This is going to be 44 over 80. And I can reduce that by 4s to, let's see here, 11 over 20. And my units on this, because they said indicate units of measure, well, if I'm doing velocity over seconds, which is essentially what's going on here, that's going to be, let's see, feet per second, so feet per second squared. So then when all is said and done, 11/20 feet per second squared. For this part of the problem, they want us to explain the meaning of the integral from 10 to 70 of v of t dt in terms of the rocket's flight. So since velocity in this problem is the rate at which the rocket's height is changing, we can say the integral of velocity is going to give us the total or net change in the rocket's height. And this is going to be in units of feet. It's going to be in height units. And this is going to be from 10 to 70 seconds. We need to put the time interval in there, or we don't get credit on one of these explain the meaning problems. All right, so the other part of the problem here, they wanted us to use a midpoint Riemann sum with 3 subintervals to approximate that integral that we just talked about. So we're going to say that this integral is approximately equal to the following. So now we're going to have 3 base times height areas that we're adding together. So for the first interval here, and they wanted us to use intervals of equal length, so we're going to be going from 10 to 30, 30 to 50, and then 50 to 70. So the 10 to 30 interval, the rectangle based off of that with this Riemann sum, we're going to have a base of 20, and we're going to multiply that by the height of, well, let's see, what height should we use for this rectangle? Since it's a midpoint Riemann sum, we always use the height that goes with the middle input value. In this case, the middle input value is 20, and the rectangle height, which is a velocity value that goes with that, is this 22. So we have a base of 20 times a rectangle height of 22. Next, from 30 to 50, base of 20 times the rectangle height 35. And then from 50 to 70, we have a base of 20 and a height of 44 for the rectangle. And again, when I say height, I'm talking about the height of the rectangle if you were to actually, graph this thing out. I'm not talking about the height of the rocket, because these output values, the heights of these rectangles that I'm talking about down here, are really velocity values of the rocket. So this does not need to be simplified. You could stick feet on the end of this and call it a day. But if we did simplify it without a calculator, probably the easiest way to do that would be to just add up all these things that 20 is being multiplied by, and then multiply that sum by 20, or basically factor a 20 out of here. So we have 22 plus 35, which is 57, plus 44 is going to be 101. 101 times 2 would be 202. Throw another 20 on the end, or it's 0 on the end because we're multiplying by 20, and that's 2,020 feet that our rocket goes. For this last part of the problem, we have another rocket, rocket B, launched upward with an acceleration of 3 over radical t plus 1. And at time 0, initial height of the rocket is 0 feet, and the initial velocity is 2 feet. We want to know which of the 2 rockets is traveling faster at 80 seconds. So we need to figure out basically velocity at 80 seconds for each of these rockets and compare them. Let's do rocket A first, because we already know a little bit about that. The velocity of rocket A is just this v of t function up here. So the velocity at 80 seconds for rocket A is just going to be v of 80, which we can read directly out of this table. That's going to be 49, and that's in units of feet per second, although I'm not going to bother writing the units because we're just comparing these now. We're not actually giving this as a final answer. Now for the velocity of rocket B, we're going to use the fundamental theorem on this. We have the rate at which rocket B's velocity is changing. That's this acceleration here. We have an initial value for the velocity of the rocket at time 0. That's this 2 feet. So I can say velocity of rocket B is going to be my initial velocity of 2 feet plus the change in velocity over 80 seconds, which is just the integral from 0 to 80 of this a of t function, which I'm going to rewrite just to make it a little easier on myself as 3 times parentheses t plus 1 raised to the negative 1/2 power dt. There we go. So this is really 3 over the square root of t plus 1. But I rewrote it like this because I'm about to take the antiderivative and use my fundamental theorem to evaluate this integral. All right, so I've got 2 plus whatever the antiderivative of this thing is, evaluated from 0 to 80. Using my reverse power rule, this bumps up to a positive 1/2. Dividing by 1/2, we're really multiplying by 2. So this is going to be 6 times t plus 1 to the 1/2 power. And again, we're evaluating that from 0 to 80. So I've got 2 plus, and now I've got, let's see here, I'm actually going to take a 6 out of that evaluation box as well. And inside, I'm going to have the square root of 80 plus 1 minus the square root of 0 plus 1. So this is 2 plus 6 times, well, let's see, this is really 9 minus 1 inside there. So we have 2 plus 6 times 8. That's, let's see, 6 times 8 is 48, plus 2 is 50. So this is the velocity of rocket B. 49 was the velocity of rocket A. The velocity of rocket B, 50, is greater than 49. And let me specify up here that this is rocket B. There we go. Now we're a little more clear. So 50 is greater than 49. This tells us that rocket B has a faster speed at time 80 than does rocket A. For this free response problem, we have a squirrel starting at building A at time 0 and traveling along a straight horizontal wire connected to building B. From time 0 to 18, and there's no units at all on this problem, the squirrel's velocity is shown in this graph here. So our first task, we want to know at what times in the interval from 0 to 18, if any, does our squirrel change direction. So we've been given a graph of velocity. And velocity, one thing that it tells you is the direction you're going, depending on the sign of the velocity. So if we're looking for a change in direction of the squirrel, we're really asking, at what time does velocity change sign on this graph? Well, v here is going to change sign at time equals 9, and also this other x-axis crossing time 15. So for that reason, the squirrel is changing direction at times 9 and 15. For this part of the problem, we want to know at what time in the interval 0 to 18 is the squirrel farthest from building A, and then how far is the squirrel at that time. So for this, we're essentially trying to maximize or minimize the position function for this squirrel. So we're going to use the candidates test on this. We're going to have to test out the distance of the squirrel from building A at the endpoints, 0 and also time 18, and we'll also have to check out critical values. Now for critical values, that's just where your velocity on this equals 0, and we already saw on part A that that was happening, well, we didn't say equals 0, but velocity does equal 0 at times 9 and 15. On part A, we said that velocity changes signs at those times, but this is also the only places where velocity equals 0. So these are our 2 more candidates for our candidates test. At this point now, we're going to test out times 0, 9, 15, and 18 in the position function. We don't have an explicit position function, but we're going to just kind of build it as we go. I'm going to call this S. So S of 0, that's the position of the squirrel at time 0. The squirrel is at building A, so we would say that our distance from building A is going to just be 0 at that time. Now to get the position of the squirrel at time 9, that's going to be my initial position of 0, plus, now we need to take the integral of the velocity of the squirrel from time 0 to time 9. The velocity gives us the rate at the at which the squirrel's position is changing. So this is going to be the initial position plus the net change in position of the squirrel. So integral from 0 to 9, that's essentially just the area under the velocity curve on the graph. That's going to be a trapezoid with a base of 9 plus a base of 5 divided by 2 times a height of 20. So 20 over 2 is going to give us 10. That's 10 times 14, so 140. And we don't know the units on this, so that's just 140 whatevers, maybe feet, I don't know. Don't really care either. Let's keep going. So definitely 140 is the winner at this point, but let's see now how far away the squirrel is at time 15. So at time 15, that's going to be the time at time 9 here, plus the integral, so we've got 140, plus the integral from 9 to 15 of velocity. So 9 to 15, we're just adding in another trapezoid. Since this is under the x-axis, or the t-axis, I guess, in this case, this is going to be a negative area trapezoid. So we're subtracting a trapezoid with a base of, let's see, from 9 to 15, that's going to be 6. And down here from 10 to 14, that's 4. So 6 plus 4 over 2 times a height of 10. So we've got 10 divided by 2 is 5. That's 5 times 10, which is 50. So this is 140 minus 50. Comes out to 90. So that is not the winning value on this. But we have one more to go here, because the squirrel was still moving between times 15 and 18. So to get S of 18, and I'm pretty sure this is not going to be the winner, but let's check it out anyway, because that's the whole point of the candidates test, is that everybody gets an equal chance at being the winner. So we got the position at 15, which we said was 90, plus I need the integral now from 15 to 18 of velocity. So that's 90 plus yet another trapezoid. This one has a base of, let's see here, 3 and a base of 2. So 3 plus 2 over 2 times a height of 10. So 10 over 2 gives us 5. 5 times 5 is 25. So 90 plus 25 is going to be 115. And out of all these values, it looks like 140 is the biggest. So the squirrel is going to be furthest from building A at time 9 with a distance of 140. On this part of the problem, we want to find the total distance the squirrel travels during the interval from 0 to 18. So for that, we need the integral of velocity, the absolute value of velocity from 0 to 18. So basically, we're just taking all those trapezoid areas and making them positive. We already added up these trapezoid areas when we were doing part B, so now we're just taking positive versions of each of them. This first trapezoid, remember, from 0 to 9, that had a value of 140. We had a base of 9 plus a base of 5 over 2 times a height of 20. So that was essentially, let's see here, 7 times 20 was 140. And now for this next trapezoid, this was a base of, let's see, from 9 to 15. That was a base of 6 plus a base of 4 divided by 2. So that's going to be 5 times a height of 10 was 50. Now we're going to add 50 instead of subtracting it, like we did in part B. And this last trapezoid, you might remember from part B, that had a value of 25 altogether. We had a base of 2 plus a base of 3 divided by 2 times 10. So that ended up being 5 times 5, which was 25. So altogether, the total distance traveled by our squirrel is going to be, let's see here, we've got 190 plus another 25 is going to be 215, whatever distance units we're doing here. Squirrel feet. So up to this point in this free response problem, the problems have mostly been like the squirrel involved, kind of small and cute. Things are about to get real ugly real quickly, though. They want us to write expressions for the squirrel's acceleration, velocity, and distance from building A, valid only on the time interval from 7 to 10, so this limited interval in here. Well, the good news is we don't have to do it for the whole function, because that would be kind of annoying with this piecewise business going on. So we're just doing it for a small piece. So let's talk about the acceleration first. So acceleration, that's just going to be the slope of velocity from time 7 to time 10. And to find that out, since it's just a straight line here, we can just use the slope formula. So we're going to have, let's see, the y value negative 10 minus the y value 20 over, and I say y value, I mean v value, output value of negative 10 minus 20, over the input value 10 minus 7. So v prime, which is the same as acceleration, again, just using our slope formula. So this is going to be negative 30 over 3, which we can reduce to negative 10. So that's our acceleration formula. It's just a constant value of negative 10. Now for the velocity function itself, the velocity function is essentially going to be the equation of the line that goes through these points here. So for that, I'm going to use point slope form, basically y minus y1 equals m times x minus x1. So y in this case is v of t, and x in this case is t. So y minus y1, I'm gonna use the point here 7 comma 20. So I'm gonna have v of t minus the y value, or the output value 20, equals my slope, which I just found, that was the acceleration. So equals my slope of negative 10, and x minus x1 is just going to be t minus this input value up here of 7. At this point, all I have to do is isolate v of t. So I can do that. Well, let me clean up the right side as well. So I'm going to distribute this negative 10. So I've got negative 10t plus 70, and then I'm going to add another 20 over there to get plus 90. So there's my velocity. Now we have to get the distance. So the distance on the interval from 7 to 10 is going to be the total distance that I've traveled, or the squirrel has traveled. I haven't been walking on this wire, but the total distance the squirrel has traveled from time 0 to time 7, plus the integral of velocity from 7 to whatever value between 7 and 10 you're dealing with. So I'm going to write x of t equals x of 7, which I'm going to officially define in a second here, plus the integral from 7 to t of, and now I'm just doing velocity, but I need a different variable, so I'm going to use u. So integral from 7 to t of v of u du, because you're not allowed to use the same variable in your limit of integration and your dummy variable inside the integral. So now let's get a little more specific about this. X of 7, that's the area under the velocity curve from 0 to 7. So that's a trapezoid with a base of 7 plus a base of 5 all over 2 times a height of 20. And we'll actually simplify that in a moment here. We don't have to, but we're going to. Plus, now I'm taking the antiderivative, the integral from 7 to t of, let's see here, the equation of velocity. We actually wrote the equation of velocity that was valid from 7 to 10. That was this up here. And by the way, this is the reason we're doing things in the order that they gave us. We needed the acceleration to get the slope of velocity for this function, and now we need the equation of velocity to actually figure out position. So I'm doing integral from 7 to 10 of negative, I'm going to write it negative 10u plus 90 du. And now let's get a little more specific about all of this. So this trapezoidal business, this is going to be, let's see, 20 over 2 is 10, times 12 is 120. And my antiderivative here, I'm going to have, let's see, this bumps up to a 2. Dividing by that, I've got negative 5t squared. Well, actually, let me do u squared first. So negative 5u squared plus, this will be 90u. And I'm evaluating that from 7 to t. So I have 120 plus all of this stuff with t plugged in, minus all of this stuff with 7 plugged in. Let's keep going here. I actually could leave it like this now, because I've got something in terms of t and the rest of its constants, but I feel bad leaving it in this state, so let's get it a little bit nicer looking. So let's see here. We've got 120 minus 5t squared plus 90t. So I'll just take all that stuff out of the bracket. Now over here, this is going to be, let's see here, 49 times 5 is going to be 245. Minus minus gives us a plus 245. And then minus 630, because I'm doing 90 times 70, which is 630, and we have a minus out here. Cleaning this up still further, we've got 120 plus 245. That's going to be 365. And 365 minus 630. Let's see here. If you do the math on that one, all of this is going to come out to negative 5t squared plus 90t, and then this will be a minus 265. You can double check the arithmetic on that, but there we go. For this calculator-based free response problem, we have an object moving along the x-axis with initial position of 2 at time 0. Velocity is given by this v of t function. First task is to find the acceleration of the object at time 4. So since I'm doing velocity here, since I already have velocity, the function for that, and I'm allowed to use a calculator, if I wanted to, I could just take the derivative of this function at 4 on my calculator and call it a day. But just kind of reading ahead in this problem, I know I'm going to need to know what the acceleration function looks like algebraically. So I'm actually going to go ahead and define the acceleration function at this point and just plug 4 into that by hand. So let's see here. I've got acceleration is really going to be v prime of t, which is going to be, this is going to be cosine of pi over 3t times a tail of pi over 3. So pi over 3 cosine of pi over 3t. And now just plugging 4 into all of that, that's going to be pi over 3 times cosine of 4 pi over 3. Well, 4 pi over 3, that's really, let's see here, 180 divided by 3 is 60, times 4 is 240. That's essentially the quadrant 3 version of 60 degrees. Cosine of 60 is 1/2, but in quadrant 3, cosine's negative. So all that together is going to be negative 1/2 times pi over 3, which is going to come out to negative pi over 6 for the acceleration on this. And there were no units, so we're done with this part. For this part of the problem, we're being given two statements. Statement 1, for times 3 to 4.5, velocity is decreasing. And statement 2, for same time interval, speed is increasing. So we're talking about the velocity and the speed of the object. And we want to know if either or both of these are correct and why it is it or isn't. All right, so this is a calculator question. The quickest way to answer both of these is going to be to graph out my velocity, and I'm also going to need to know about what the acceleration is doing on this time interval to really effectively answer both of these. So let me go to my calculator. So here I am in the y equals of my calculator, and in y1 I've put the velocity function that they gave me. Now I also need to graph out the acceleration and see what that's doing in terms of the sign of the acceleration. And I already defined acceleration back in part A. I didn't really have to, but I did it back there. And you might remember that that was, let's see here, fancy fraction. We had pi over 3. So pi over 3 cosine of pi over 3 x. There we go. Pi, takes a while to enter these in here. X, there we go. So there was our acceleration function. And we're just going to graph both of these and see what they're doing on the interval from 3 to 4.5. So let me go to Window, and I'll do x min as 3, x max as 4.5. And let me do zoom 0, zoom fit. Let's get a look at both of these functions. So this first one, this is our velocity function for the particle. And this second one is our acceleration function. There we go. So one thing I noticed, and there was the graph I just drew, is that for the time interval from 3 to 4.5 at least, the velocity is less than 0, and so is the acceleration. So these are two very important pieces of information that I'm now going to use to justify what I say for statements 1 and 2. So for statement 1, they're talking about whether the velocity is increasing or decreasing. Since acceleration is negative, that tells us that the velocity is going to be decreasing on this interval. So that means that statement 1 is actually true, and that's why. Now for the speed, we have to compare the signs of velocity and acceleration. We see that they have the same sign, they're both negative. Therefore, the speed is going to be increasing because they are working together. So that means that statement 2 is also true. So both statements end up being true. For this part of the problem, they just want the total distance traveled by the object on the interval from 0 to 4. Since I am allowed to use a calculator on this, I'm just going to do the integral of the absolute value of velocity from 0 to 4. That's my standard total distance setup. I'm just going to do that whole thing on the calculator. So here's what this looks like on my calculator. I did Math 9 to get integral. I went from 0 to 4. Absolute value, if you do alpha window, there's a little submenu with abs in it. And then for y1, I just did alpha trace and pulled y1 out of that menu. Put a dx over there, press enter, and we get 2.387, and there's no units at all in this problem, so it's just plain old 2.387, and we're done. On this last part of the problem, they just want the position of our object at time 4. So just using our FTC, we're going to have the initial position, which was 2 at time 0, plus the integral from 0 to 4 of our velocity. And they already defined velocity, so I don't have to write out anything other than v of t dt in there. And now the rest of this just happens on the calculator. So here's what this looks like on my calculator. I have 2 plus, I did Math 9 for integral, 0 to 4. I did alpha trace y1, because that's where I stored my velocity function, dx, and press enter. That's about 3.432. There we are.